Okay, so we left off right before example 3 yesterday. We were doing a Taylor-Maclaurin series, different from polynomials, but very, very, very similar. The difference being polynomials are approximations, finite number of terms. Series are exact approximations, infinite number of terms, and they represent functions either for all real numbers on some specified interval, which is a certain radius from the center, or only at the center. Those are the only three things. Okay. So we can do what we did before. We can generate our own Taylor series centered at C like we did for polynomials the exact same way. This is the important thing right here. This is the nth term, the rule of sequence. It's the nth derivative at the center over n factorial times x minus the center to the nth power, and then plus dot, dot, dot. Okay? And of course, if it's centered at 0, it's called a Maclaurin series. So let's go ahead and try it out. Okay? One of the things you're going to have to do is generate it for functions at different centers. So here's one. Find a Taylor series for e to the 5x, which if it was centered at 0, we could just write out the one for e to the x and plug in a 5x, but it's centered at 2. So that's a different center. So it says give the first 4 non-zero terms, so they don't specify the degree, just the first 4 non-zero terms, and they ask you for the general term, which means the nth term. So you're going to have to get the rule of sequence. So what do we need to get over here? We need to get our coefficients of the numerators. Like we did before, we get the machineries up and running. So the center is 5. That's kind of the most important number here. So let's go ahead and do that. F of x is e to the 5x, and so f of 5 is e to the 25. What a beautiful number. Kind of big. Kind of big. Is this what? The center was 2. Oh, not 5. Okay, I'm sorry. I've got other things in my mind. Why did I pick 5? Because 5's right there. Thank you. Golly. Okay. Did I mention today after school is hall decorating? That was an alert from my phone. All kinds of things going on. All right. 5 times 2 is 10. Okay, we are back in business. I don't even think we got started to be in business to begin with, but now we're warming up. The oil is at like 100 degrees. All right. F prime of x. Don't tell me. It's 5e to the 5x, yes? Yeah. Okay, sweet. All right, so I'm back in the groove. F prime of not x, but the center 2. Oops. I'm back out of the groove. I just need to change that one up there to a 2. There we go. And now it's 5e to the 10th. The second derivative is 5 squared e to the 5x. I'm just going to leave it like that instead of 25. So then f double prime of 2 is 5 squared e to the 10th. And we need to give the first 4 non-zero terms. I'll go one more. You might be able to stop there and see a pattern, but that's fine. The next derivative is going to be 5 cubed because of the chain rule. It generates another 5. And f triple prime of 2 is 5 cubed e to the 10th. Very good. Yeah, whatever derivative we are, the nth derivative, it's 5 to the nth power. So that's the pattern that you want to kind of keep instead of just simplifying the 5. And it looks like it's always e to the 10th. So here we go. We can say then that e to the 5x, would we put equals or squiggles? Find a Taylor what? Series, not polynomial, which means it is equals. Okay, if it said Taylor polynomial, it would give you the degree. If it says series, it's going to say how many terms. So it's an equal sign. All right, so we'll start off like we would do with the tangent line. It's the y value, e to the 10th, plus the slope, which is 5e to the 10th, times x minus the x value of 2. Pattern doesn't pick up to the second derivative. So there we are. The second derivative's coefficient numerator is 5 squared e to the 10th over 2 factorial. Don't forget that. Times x minus 2 squared. That's 3 terms, so we need one more. So plus 5 cubed e to the 10th over 3 factorial times x minus 2 cubed. Now we would stop there if it were a polynomial, but again, this is a series. So now we would have to say plus dot, 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 and then plus, and this is where the pattern's important, which y'all have already seen. It's 5 to the n e to the 10th over n factorial times x minus 2 to the nth, and then we put another plus yada, yada, yada at the end. All right, so in the first section of Chapter 9, we did a little bit of this trying to make sense of some patterns, and that was kind of for this purpose, finding the nth term. Now, if you want, you can collapse it down. Let's see what that would look like. If you collapse it down, it's going to start at some n value. It's going to go to infinity. It's going to be the nth term over n factorial times x minus 2 to the nth. And remember, bless you, all we have to do is make sure we start at the correct value of n. So if our first term needs to be the constant, e to the 10th, we would need to start at 0, not 1. Yeah, okay, very important. Again, if you leave it like this, the nth term, you don't need to specify what n you're starting on. But when you put it in collapse form, and there's another chair there, you do have to do that. Okay, are we done? Yeah, that's all it asks us to do. Okay, that's all it asks us to do. We could go on and find the radius of convergence for this. You want to go ahead and do that? It doesn't ask us to do that, but hey, it's sprinkling. Let's go above and beyond. All right, so what test are we going to use for the interval of convergence? The ratio test. Sweet. So let's go ahead and do that right here. Ratio test. For that, you just need the nth term, so it doesn't really matter which one. I like to get the one from the condensed series form. All right, so here we go. It's the limit as n goes to infinity. What do y'all think it is before we start? You think it's all real numbers, or do you think it's some kind of interval? You think it's an interval. Okay. Well, remember, what was e? E to the x converged for all real numbers. Would e to the 5x, if we change the center, be the same? We'll see. And then it's x minus 2. I'm going to throw that in the numerator to the n plus 1. So that would be the n plus first term. We have 3 n's, so they all become n plus 1. Times the reciprocal of the given one, n factorial, 5 to the n, e to the 10th, and then x minus 2 to the nth will now be in the denominator. And then the fun part, all that simplifying. We have one more factor of 5 in the top, e to the 10th, see ya, wouldn't want to be ya. We have one more factor of x minus 2 in the top, and we have an n plus 1 in the bottom. That's all that's left. And so remember, the variable for the limit is n. We treat x or x minus 2 as a constant. So the numerator is essentially a constant. The denominator is n plus 1. What happens to a constant over something that grows infinitely large? It approaches 0, which is less than 1 for all x, right? For all x. So the interval of convergence is what? Very good. It's all real numbers. Convergence. But we want to go ahead and list it as an interval. Is negative infinity to infinity. Or we could say the domain of the series is all real numbers. And just for kicks and giggles, what would be the radius of convergence? Not all real numbers, but infinity. Right. Yeah, it goes infinity in both directions from 2. So yeah, for these functions like e to the x or even different versions of e to the x, they're gonna truly equal the function they represent for all values. Okay, and that's important. We put an equal sign, not a squiggles. All right, cool. Comments or questions on that? All righty. Let's see. There are 4 special Maclaurin series that you must know. These are the series for e to the x, sine of x, and cosine of x. And we've kind of already memorized, or you should have memorized, their Taylor polynomial forms, or Maclaurin forms, actually they are. So the series is not going to be that much different. And then there's one more. Right, yeah, I know. And then 1 over 1 minus x. Thank you. Yeah, I was going to hold off on that one because this one has its own special section in the next section, okay? So we're going to deal with 1 over 1 minus x exclusively in the next section. But in this section, we're going to deal with e, sine, and cosine. So as we saw yesterday, Skylar kind of brought it up, when we take the derivative of things, they basically act the same way that the original functions would. And we can also integrate them. But when we do that, for functions that don't converge for all real numbers, we have to be considerate of one thing. Okay? Now, e to the x and sine of x and cosine x don't apply because their domain is all real numbers. But 1 over 1 minus x, notice x can't equal 1, right? It's not in the domain of the function. So there's no way the polynomial function that represents it is going to be the same value at 1. Okay? So for functions that have a limited interval of convergence, when we take the derivative or integrate, we will not change the radius of convergence. They're going to act the same way on the open interval. However, it may change the behavior at the endpoints of the interval. Okay? And a good example, there's another, just deal with it. It's kind of fun. Scooby-Doo every once in a while. Like if we had x to the 1/3, the domain is all real numbers, yeah? But when we take its derivative, we get 1 over 3 to the x to the 2/3, which now x cannot equal 0. So some things can change. When you take the derivative and you take the integral, things can change. So it's not going to change on the open interval, so we don't have to change the radius of convergence. But when we take the derivative or the integral of a series that represents a function on a limited domain, we will have to retest the endpoints, okay? We need to retest the endpoints. Let me just write that. Retest endpoints. You don't have to do that if there are no endpoints, all real numbers, okay? So now that we've memorized those, here's what we can do. We did a little bit at the end of the previous section. We can substitute into a series for x. So like we can replace x with 3x as long as the center is the same. We can multiply or divide by a constant, like we multiply through by a 4, I think, and we can even multiply through by a variable like x. We can even add or subtract two series. That's kind of interesting. The way that you would add or subtract two series is not side by side, but if you add them vertically, you can add like terms. And some of the terms may combine or some of them may cancel out. Okay, we'll see that here in a little bit. We can, of course, differentiate or integrate a series, and as I just mentioned, we'll have to retest the endpoints. And number 5, we can recognize the series as a geometric power series, kind of like we did up here, kind of like we did way up here, where we could have recognized it as geometric from the beginning. Okay, let's go ahead and write them out. The three in this section we need to know. With the nth term, you need to know the nth term. So e to the x is, again, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I'll write out the first 4 non-zero terms so you can see the pattern. And then plus dot, dot, dot. I think we did this one earlier in this section. The nth term is x to the n over n factorial plus dot, dot, dot. And then I'm going to write it in the condensed form. Sigma from n equals 0 to infinity of x to the n over n factorial. Okay, so there's e to the x. Memorize it, memorize it. Sine of x, what type of function is sine? Even, odd, or neither? Odd. So it starts with x to the first odd power, and then it alternates, remember, minus x cubed over 3 factorial. That looks ugly. And then plus x to the 5th over 5 factorial. Bless you, minus x to the 7th over 7 factorial, plus dot, 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 plus. Now, we haven't done the nth term for this one yet. So notice the first 4 non-zero terms of this one make a 7th degree, and the first 4 non-zero terms of e to the x make a 3rd degree. So that's why with polynomials, they'll always specify the degree, whereas with a series, you'll always specify the number of terms. First of all, it is an alternating series, right? So let's go ahead and throw an alternator in there. It's -1 to the either n or n plus 1. I'm going to have to come back and match that up. I'm going to match that up later so that I get the right sign, depending on where I start. Okay, so it's either n or n plus 1. I'm not sure. Now let's go ahead and get the powers of x. It looks like that's going to be times x to the. If all the powers are odd, how do we generate odd numbers? 2n plus 1 or 2n minus 1, either way. Again, it's just going to depend on where your n is that you start with. I like 2n plus 1. Okay? And then it's all over the same number, right? So it's all over 2n plus 1. Factorial. All right, so here's what we need to do. Well, plus dot, dot, dot at the end. Now I just need to make sure that when I plug in the right value of n to get the first term, the sign matches up. So in order to get x to the first, I have to plug in a what for n first? I want my first term to be x, so I need to plug in, if I plugged in a 1 for n, I would get x cubed, right? So I do have to start with n equals 0. So that's going to make this stuff match up with the first term. So what does it need to be then? Does it need to be -1 to the n or n plus 1 to make my first term positive? Well, if I plugged in a 0 for n, negative 1 to the 0 would be positive 1, right? So it would just be n. If the first term were negative, I would need that to be n plus 1, okay, when I start with 0. So there's a couple things to consider here. All right, you're trying to get it to match up with the x's, and then you get the sign correct. So it's just negative 1 to the n. There is the nth term, so now we can write it in condensed notation. That equals sigma from n equals 0. We've already done that analysis of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. And the reason you want to memorize the nth terms is because, as you'll see here, when we take the derivative and integral of each term to find the new nth term, we can actually just manipulate the nth term in the same way. And we don't have to kind of come up with a new pattern. All right, and then, of course, the derivative of that is cosine. So if you ever forget cosine and remember sine, you can take the derivative. But cosine is probably worth remembering on its own. It's an even or odd function. Even. So the first even term would be 1x to the 0th power, so just 1. And then it alternates x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So it too alternates. So plus dot 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 plus, let's get our alternator in there. It's either negative 1 to the n or n plus 1. How do we generate even numbers? X to the 2n, yeah, all over 2n factorial. Make sure you have parentheses around the 2n plus dot dot dot. And now, and again, in order to get my first term to be a 1, my n has to start with 0. And in order then to get my first term to be positive, it has to again be negative 1 to the n. If the first term were negative, it'd be n plus 1. So that looks like that works. So you're checking two things. You're checking to see where you start to get that to be the first term, and then you check to whether or not you need to adjust this, because you can easily adjust that to an n or an n plus 1 so that the signs match up as well. All right, so then if we write that in condensed form, n equals 0, we've already considered that, to infinity, negative 1 to the n, x to the 2n, all over 2n factorial. All right, so memorize those, memorize those, memorize those. You probably have the pattern memorized already. The nth term is not that real difficult to come up with, so I can see you not wanting to memorize that. Okay, and then we'll get to 1 over 1 minus x in the next section. Now, example 4 is going to be kind of anticlimactic because we kind of did a little bit of it yesterday. If f of x is that, do you recognize that guy? Maybe. Yeah, maybe you do. I don't know if you do. I don't really recognize it. I'm on my off day today. Let's find f prime and f prime is 0. All right, so first of all, this is an infinite series, right? Is it Maclaurin or Taylor? Maclaurin and Taylor, right? Technically. Yeah, but it's a Maclaurin or a Taylor centered at 0 because it's just x. So let's take the derivative like they said, and this is exactly what we did yesterday, so I can see if you don't want to write it. We kind of got to the moment because it came up naturally, which is fine. But again, plus dot dot dot, I can modify the nth term, n x to the n minus 1 over n factorial plus dot dot dot. And if we manipulate that, we get 1 plus x over 2 factorial plus that's x squared over 2 factorial when they divide out. Plus, notice we lost a term, so we no longer have 4 non-zero terms. So if it asks you to find the first 4 non-zero terms of the derivative, I just x, yeah, sorry. X, thank you. Thinking of my next point. It's okay, I've had better days, it's okay. My eyeballs hurt. That's a weird feeling for me. My eyeballs, like they're like someone squeezing them in the back. Is that a migraine? I don't know, I don't get migraines. Is that a migraine? Okay, cool. Something new. Yay. Anyway, you have to be careful. If it says to find the first 4 non-zero terms of the derivative and we stop there, would we have it? No. So then you would need to volunteer another term by seeing the pattern, which we would anticipate to be x cubed over 3 factorial plus dot dot dot. And then as we saw yesterday, this simplifies to x to the n minus 1 over n minus 1 factorial. And it still captures the pattern of what's going to turn out to be, I guess, e to the x, but it starts at a different value of n, okay, if you wrote it in condensed form. Okay, and because it's a Maclaurin series, it should have the exact same value at the center, which is 0, as the function it represents. So yes, you do recognize this as e to the x. Okay, we do recognize that as e to the x. So what is e to the 0? 1, okay? So what should f prime of 0 be? It should also be 1. So that's 1 plus 0 plus 0 plus 0 forevermore, and lo and behold, it's 1. Okay, nice. Yeah, if you wanted to plug in e, you would get e to the e's power. And if you did f prime of e, you'd get 1 plus e squared over e factorial, which ends up being e to the e's power. How do we know that? Because the interval of convergence is all real numbers, right? Okay, and so when we take the derivative, it's going to be the exact same domain, all real numbers, because there's no endpoints to check. All right, kind of cool. Yes, we do recognize that. All right, let's try this guy. If f of x is equal to negative x plus x cubed over 3 factorial minus x to the 5th plus yada, 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 and big F of x is the integral of that, and big F of 0 is 1, find big F of x. What? That kind of looks like negative sine. Good eyeballs. Better than mine today. Yeah, that looks like sine, but the terms alternate alternatively. Okay? Yeah, so that would be a negative 1 times sine. So yeah, very good. So this is a pretty typical thing. It says, let big F be the antiderivative of this. So they're giving us an initial condition. Let's go ahead and find it by finding the antiderivative. So if I take the antiderivative of both sides, the antiderivative of f of x dx is going to equal what we're calling big F of x. And now let's just go ahead and write each term. What would be the antiderivative of negative x? Just polynomials here. Yeah, negative 1/2 x squared or x squared over 2. When we had just regular functions, I would probably write it as negative 1/2 x squared. But for Taylor series, it's kind of nice to have the x's in the top. Okay, cool. And the next one would be x to the 4th over 4 times 3 factorial. What's 4 times 3 factorial? 4 factorial. Hey, 2 is the same as 2 factorial. Just saying. And then it'd be minus, and then you take the antiderivative and you get x to the 6th over 6. 6 times 5 factorial is 6 factorial. Yay. All right, so now we go plus dot, dot, dot. And we can do the same thing with the nth term. So negative 1 to the n plus 1 with a little asterisk there. You always want to come back and check the alternator to see if the signs work out correctly. And I could do the same thing here. I could say that's x to the 2n plus 1, which makes it 2n plus 2, all over 2n plus 2 times 2n plus 1 factorial, which is 2n plus 2 factorial plus dot, dot, dot. All right? And then some players, we need to add what at the end of our antiderivative? Plus c plus dot, dot, dot. Yikes. Where would have been, perhaps in hindsight, a better place to put the plus c, the constant? At the beginning. Very good, because we write things in increasing order now, but you can throw it in the back there. That's fine. Whatever you want to do. Now let's check the alternator here. In order to get my first term, this right here has to give me an x squared, which means I'm starting with n equals what? 0 or 1? In order to get an x squared to start with? 0. So for this, I have to start with n equals 0. Will that still work here sign-wise? If I plug in a 0 for n, do I still get a negative number? Yeah, okay. So just always check that sign on the alternator and make sure it works. Okay, now how are we going to find c? We need an initial condition, don't we? It gave us one at the point 0, 1. So at the point 0, 1, we can plug it in. So we set it equal to 1, and we plug in a 0 for x, and we get 0 plus 0 minus 0 plus da 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 plus c plus 0 plus 0. Yeah, that looks like c equals 1. So big F of x is, I'm going to throw the 1 in the front now this time. You okay with that? So it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot 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 negative 1 to the n plus 1 asterisk, we just changed the first term, asterisk, x to the 2n plus 2 all over 2n plus 2 factorial plus dot dot dot. Does that work? What does n need to be now so that the first term, yeah, it actually needs to be a negative 1. That's kind of gross, right? But if n were negative 1, does that still work when I do that? If I plug a negative 1 in there, I get negative 1 plus 1 is 0. Negative 1 to the 0 is positive, so it still works, yeah. So again, you don't have to worry about that unless you're condensing it. And it's okay to start at n equals negative 1. It's just not real typical. So what you could do if you wanted to get rid of that is you could just replace n with n plus 1. And you'll just then have to do a little bit more math. Same thing, yeah. Replace that n with an n plus 1, and you're advancing it one more down the line. Yeah. So I'm just going to leave it like that. Now, do you recognize this function? That's cosine. So big F of x is actually equal to cosine. And is that surprising? No. Gorel was all over it in the beginning. Little f of x was equal to negative sine of x. And what is the antiderivative of negative sine of x? Cosine of x, yeah. Very good. All right. Yes. Well, we're learning a process right now, and I'm choosing the familiar functions on purpose so that you can verify it against what we know. But later on, that's not going to be the case. Later on, we're not going to recognize the functions, and we're going to have to trust our work. Yeah. So, yeah, if I did ask you this, you could be like, oh, yeah, no problem. Okay. All right. Any questions or comments on that? Okay. Example 6. Find a Mac series for sine of x squared. Find the first 4 non-zero terms in the general term. Well, because it's a Maclaurin series that's centered at 0, we don't have to reinvent the wheel here with Taylor's form, getting our coefficients for the numerators. We can just modify what we've memorized. So this is what I call building the functions. Building the functions. So let's go ahead and say that sine of x, first of all, would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Does it say to find the general term? It does. Now, you got to read carefully because sometimes the free response will not ask you to find the general term. And if you volunteer it, it has to be right. So make sure you read carefully. Most of the time they do. But on the rare occasion, they don't ask for it. So there's the first 4 non-zero terms plus dot dot dot. Plus, here's where you can kind of go a little bit faster. Negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial if you just flat out memorized it, plus dot dot dot. And now, all we have to do to build this function, since it's still centered at 0, is replace x with x squared. All right, so on the next line, we get sine of x squared. And this is substitution, not multiplication. So we get x squared minus x squared cubed is what? X to the 6 over 3 factorial plus x squared to the 5th is x to the 10th over 5 factorial minus x to the 14th, good, over 7 factorial. And because it asks you for the nth term, you don't have to try and find the new pattern from here. You can just modify this. This is negative 1 to the n. We'll do the same thing. If I replace x with x squared, let's do this over here. I get x squared to the 2n plus 1, which would become x to the what? 4n plus 2 when you multiply and distribute. That's going to be your new power, x to the 4n plus 2. All over, same thing, 4n plus 2. 4n plus 2. Oh, it's still over 2n plus 1. Thank you. Yep. Because there's no x down there. Sorry. You're good. You're good today. You guys are on fire today, and I'm not. So teamwork makes the dream work. Hey, which reminds me, hall decorating today after school. They need help. So notice if you had to go 2, 6, 10, 14, and you had to kind of find that pattern on your own, it might take you a while to come up with 4n plus 2. Okay? The common difference is 4, which means it's going to be multiplication, and then you can adjust. We've done stuff like that with sequences, but just adjusting the the existing rule of sequence is a good way to go. All right. How are we doing? We're on page 4 or 5. What time do I have to leave, Colin? 11:25? 12 minutes. Okay. Good. I didn't meet the guy yesterday. He never showed up. Okay. Notice we started right at 11:30. Yeah. Some days when I don't go down, we start, like 11:38? Okay. Example 7. Find the Maclaurin series for g of x equals x cosine of x. It's a Mach series, so it's centered at 0. Find the first 4 non-zero terms and the general term. So this is going to be another one of those build the series, okay? So let's go ahead and start with just regular old cosine x. It is an even function, so it's 1 minus x squared. I'm going to try not to mess up on this one, but I'm squinting a lot today. I don't know if they did that in the 50s or not. It's 50s day, Tyler. I know you don't know that. Plus, dot, dot, dot. Plus the nth term is negative 1 to the n times x to the 2n plus 1 all over the quantity 2n plus 1 factorial plus dot, 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 and it's just 2n. Okay, I caught it. I caught it before y'all did. I get credit for catching that one, not y'all. Okay, sweet. Breather. It's all the pollen or it's all Colin? Okay. Okay, so anyway, now we are going to multiply everything by x. So x cosine of x is x now for the first term. We're distributing it, so we're increasing the power of x by 1. So x cubed over 2 factorial plus x to the 5th over 5 factorial. Oh! We're only changing x. Why do I want to change everything? I just want to do too much. I want to change the world. 4 factorial minus x to the 7th over 6 factorial plus dot, dot, dot. Negative 1 to the n, x to the, we're adding 1, so it becomes 2n plus 1 all over, keep it, 2n factorial. Let's quickly check to see if the alternator is the same. I would need my x to start with 0, so that 2n plus 1 gave me x to the first, and negative 1 to the 0 is still positive, so that works. Okay, great. So that's not that bad, right? Without me. Y'all can do that easier without me. Thank goodness. Okay, let's keep going. We got 2 more left, and we're like getting closer to example 9, which I might save for tomorrow. That way the worksheet will have to be due Thursday. This would be like proving the Euler identity. Hey, speaking of tomorrow, tomorrow is twin day, but it's groove hippie disco twin day. It's not just show up wearing like tourist outfits and call that twinning. You have to be twinning as a hippie or disco groove twin, okay? So it's a specific type of twin. So not just any twinning, any style, hippie or disco 60, 70 twin. So try to coordinate that with someone, and if you can, you could be in the twin parade. If not, you'll just walk down and watch it and wave. Okay, sweet. Find the Maclaurin series for e to the x plus e to the negative x over 2. Find the first 4 non-zero terms and the general term. So this is another one of those building because it's a Maclaurin series. So which one are we going to start with on this one? E to the x. Let's write e to the x out. E to the x is 1 plus or minus. Does it alternate? It does not alternate. Good. 1 plus x plus, and then the pattern picks up x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 plus x to the n over n factorial plus dot, dot, dot. Did I do it right? Woo! All right. The rest of my life begins now. All right, so now let's do, what, Tyler? E to the negative x. Good. E to the negative x. This is substitution. So that becomes 1 minus x. What happens on the next term when you square the negative? It stays positive, right? Okay. Ooh, yeah. And Well, I'm gonna create e to the negative x first, and then I'm gonna add them vertically. Yeah, I'm sorry, I didn't say that. So I'm replacing x with negative x. And notice I'm stacking the terms vertically. So anytime you have an odd power, it's going to change the sign. Anytime you have an even power, it's going to keep the sign. So this becomes minus x cubed over 3 factorial plus dot 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 plus. Now you could do the same thing here. You could say it's negative x to the n over n factorial, and that would be both fine and dandy. Or you could separate them and say it's negative 1 to the n times x to the n over n factorial. Either one. Okay? I think I'm going to do that. Is that okay? I kind of like separating the alternating piece from the magnitude piece. Negative 1 to the n, x to the n. Okay. All right. So now, because I want that to be a plus sign, I'm going to draw the line right here in plus. If they were subtraction, I would distribute the negative. So now I'm getting e to the x plus e to the negative x. Okay, we're building this. Equals. And now I can add like terms in vertical columns. 1 plus 1. 2. What happens with the x terms? They cancel. Plus, I'm left with 2x squared over 2 factorial. What happens with the next ones? They cancel. It says to write the first 4 non-zero terms. I had 4 non-zero terms, but half of them canceled. I need 2 more non-zero terms. You can just assume them. Absolutely. What would the next one be? Would it be 4? We'd have 2 of them, so it'd still be twice x to the 4th over 4 factorial plus twice x to the 6th over 6 factorial. Yeah. Plus dot dot dot, what would the nth term be? Would they alternate anymore? No. So it would just be 2x to the 2n over 2n factorial. You can almost just pick up that pattern from what you're generating them, right? All right. That does simplify. If you wanted to kind of simplify that, but notice it doesn't simplify down to anything nice like 4 factorial, but you might be able to get some new numbers out of it. So what would be the last thing to do? Divide it by 2, right? Let's divide everything by 2. That's why maybe we leave those 2's up there. Let's divide everything through by 2. So every term, we're going to divide the 2 out, and we're left with 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus dot 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 plus x to the 2n over 2n factorial plus dot dot dot. Now, that is the result. Okay? It sure looks a whole heck of a stinking lot like what on the right side? It looks a lot like cosine. But it's not cosine because cosine does what? Alternates. This one doesn't alternate. This one is called, not cosine squared, it's called cosh of x instead of cosine of x. Kid you not. H stands for hyperbolic. This is what we call hyperbolic cosine. It's another function, and it is related to cosine. It's the cosine series, but all the terms are positive. Okay? And these types of curves are related to like the St. Louis arch. The St. Louis arch, is that the most famous parabola in all of mankind? The Gateway Arch? Is it a parabola? No, it's a catenary curve. A lot of people mistake it for a parabola. So what is a catenary curve? This is an inverted curve. If you were to take a weighted chain and suspend it, the way that it would hang because of gravity looks parabolic, but it's a little bit flatter near the top. And that's called a catenary curve. And so if you were to graph e to the x plus e to the negative x over 2, you would see something that resembles a parabola. Okay, but it's not. It doesn't behave the exact same way. It doesn't have the same focal properties as sine or cosine. So they call it hyperbolic cosine, and there's an entire set of derivatives that you go along with cosine, hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine, and it's also positive. So kind of interesting, right? There's some more stuff out there and applications of it. We're going to end tomorrow with proving Euler's identity, the only tattoo I would ever get if I were to get a tattoo. Okay, my favorite equation, identity in all the whole world. All right, we'll stop right there. Not the best lesson, but we got the errors worked out.